All right, starting our next topic here, looking at systems of equations. Today we're going to be looking at using substitution to solve a system. So on this warm-up here, it just says analyze each system of equations. What can you conclude about the value of y in each? So they just give us a very basic substitution we can plug in for each one. So number one, if you substituted in 12 for x, we'd have y equals 12 plus 22, and we'd get y equals 34. For number two, if x was 0, y equals 0 minus 45, so y would be negative 45. For 3, it says x equals y. Well, if x equals y, if we plug in x for y, we're going to have x equals 2x minus 10, and then we could solve for x, so we could subtract 2x, and we'd have negative x equals negative 10, and then of course divide by negative 1, and we're going to end up with x equals positive 10. And the fourth one gets into, I want to wait a little farther into the lesson to look at that one, just because that's getting into a little more difficult level of substitution that we're going to be covering today, which we haven't gotten into yet. So I don't want to look at that as a warm-up activity. So key terms, we're going to look at systems of linear equations, what that means, how the substitution method works, and what standard form of linear equation is. All right, so we're actually going to skip past the getting started activity, and we're going to go straight to activity 1.1, introduction of substitution. So it says in this lesson, we'll explore systems of equations. When two or more linear equations define a relationship between quantities, they form a system of linear equations. It says Janet was helping her mother make potato salad for the county fair and was asked to go to the market to buy fresh potatoes and onions. Sweet onions cost $1.25 per pound, and potatoes cost $1.05 per pound. Her mother told her she had to use $30 she gave her to buy these two items. So we're going to write an equation in standard form that relates the number of pounds of potatoes and the number of pounds of onions that she can buy for $30. We're going to let x represent pounds of onions and y represent pounds of potatoes. So onions were $1.25 per pound, so $1.25 times x plus $1.05 times y for pounds of potatoes equals the $30 she has to spend. So there's our equation in standard form. It says Janet's mother told her that the number of pounds of potatoes should be 8 times greater than the number of pounds of onions. So the number of pounds of potatoes, y, needs to equal 8 times the number of pounds of onions. So y equals 8x. So question 3 wants to know, will 1 pound of onions and 8 pounds of potatoes satisfy both equations in y? Well, if we first just try to plug 1, 8, so 1 for x, 8 for y, for our two variables into, I'll try first the standard form equation. So 1.25 times 1 plus 1.05 times 8 equals 30. And if we simplify that on the left side, we can just put all that in the calculator at once, all of this. We're going to get 9.65 equals 30. Well, that's not true. So without even trying the other equation, 1/8 does not satisfy both equations. And it has to satisfy both equations to be the solution to the system. So if I were to try it in the other equation, we would see that it works. Plug in 8 for y, 1 for x, and we're plugging that in again to y equals 8x. We will get 8 equals 8. So it does satisfy, that erased. You can rewind it to get that I accidentally just clicked erase, but I'll rewrite what I was just writing. So if we plug that in, we get 8 equals 8 times 1. So for that equation, it does satisfy. You get 8 equals 8, but it needs to satisfy both equations. Okay, again, if you weren't done writing that, filling that in, feel free to rewind, get back to it right before it deleted. I can't get that back for you. All right, on the next page, we're going to create a graph here. And we're going to create upper bound, lower bound. It's just kind of, this table is walking us through how we're going to create our graph here. So variable quantities, we'll say pounds of onions is our X, and our Y is pounds of potatoes. Okay, the lower bound, obviously we can't buy more than, or buy less than 0 of either one, so the lower bound is going to be 0. And then for the upper bound, I'm going to try to create it, let's see, let's make it 20. I think 20 should about work for our X, 40 for our Y, and we'll say an interval of 2, both of them. So let's see if that works. Okay, so I'm going to count by 2s on my X-axis. So that goes up to 20. And then on my Y-axis, let's see, we'll make every line 2. So the first big line here will be 4. So 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, and then 40 would be the top one. Okay, so if we were to create that, one of the equations, I'm going to do this one in red, y equals 8x, starting at 0, 0, and it's got a slope of 8, so it is going up 8 and right 1. So it'd be up 8, right 1. If we do that again, up another 8, right 1, up another 8, right 1. We're going to get a line that looks about like this. And then for the other one, let's see, I'll do that in black. We're going to have to plot that one using our X and Y intercepts would be our easiest method since it is in standard form. So my X-intercept would be where Y is 0, so that leaves me with 1.25x equals 30. And when I divide by 1.25, I'm going to get an X value of 24. So my X-intercept is 24, 0. Okay, well, that's actually a little off our graph, so I'm going to put about where it would be. So 22 is going to be about here. Okay, and then my Y-intercept, if I'm going to use this space over here, 1.05y equals 30. And follow the same steps, divide by 1.05, and we're going to get y equals 28.57. So it doesn't come out to be a nice, pretty number, nice integer for us to deal with here, which makes it a little trickier to graph. So 28.57 we could say is about right here. And if I were to try to connect those 2 points, we're going to see that it doesn't intersect, I should say, perfectly at a grid line. So can we determine the exact solution of this linear system from graphing? And the answer there would be no. The point of intersection does not fall directly on grid lines. Okay, so the whole point of looking at that was just to show that sometimes graphing isn't going to be the best method to try to see where those 2 lines cross. Often it's not going to be the best method because anytime we end up with a solution that's not integers, we're not going to be able to see where they cross on that graph. So if we were to estimate it, though, it might be a good estimate. So looking at our graph here, I'm going to estimate that point is about at 325, I'll say. So 325, I'm going to say is my estimate based off that graph. Okay, so that'll come into play here in a minute when we solve it exactly and find our solution. Okay, so the way we're going to solve it is using the substitution method. So this box here is just working out exactly how substitution works. With substitution, if we have one of the equations equal to a variable, like here we have y equals 8x, we can go sub in 8x to where y is. And if we plug in 8x for y there, now we have an equation with just one variable You can see here. And if we have an equation with one variable, we can solve for that variable. And once we find x, then we can go plug it back in to either equation and solve for y. And that's what we're going to do here using substitution. So if we go on to the next page, it wants us to check to see if that solution is correct from this worked example. So they got an x of 3.1 and a y of 24.8. Well, if we go plug that in to the first equation, 1.25, 3.1 for x, plus 1.05 times 24.8 for the y equals 30. Well, if we simplify that, again, we can just put all this in the calculator. We are going to get 29.915 equals 30. So again, we had to round a little bit here. So looking at what we ended up with, I'd say yes, that did work and find a point that is a solution to that system. And if we try it with y equals 8x, so y 24.8 equals 8 times 3.1, and we will get 24.8 equals 24.8. So that one matches up perfectly. So definitely good there. And again, only a rounding error causes it to not be exactly 30 on the other equation. So what is the solution to the system and what does it represent in terms of the problem? So the solution was the 3.1 for x, 24.8 for y. And what is that representing? It's representing that for $30, Janet should buy 3.1 pounds of onions and 24.8 pounds of potatoes. So comparing our solutions, if we were to round that answer, let's call it 325. Comes out pretty close to what my estimate was. I estimated 325, so I got lucky there. Most of the time, we're not going to be exactly to the correct answer, but my estimate came out to be right at what our solution was, 325. So sometimes being lucky is better than good, but you can see at least an estimate. The graph provides a really good estimate. We just can't necessarily always get it exact. So we're not going to be so lucky every time that our estimate turns out to be exactly what our solution is. All right, for activity 1.2, Samson and Adrian are helping to set up booths at the fair. They're each paid $7 per hour to carry the wood that is needed, build various booths. Samson arrives at 7 a.m. and begins working immediately. Adrian arrives 90 minutes later and starts working. So we're going to write an equation that gives the amount of money that Samson will earn, y, in terms of the number of hours he works, x. So Samson's the one arriving first. So his equation, y, the amount of money he will earn, is equal to $7 per hour times x, the number of hours. So how much money will Samson earn after 90 minutes of work before Adrian's even showed up? Well, 90 minutes is 1.5 hours. So 1.5 times 7. So he will have already made $10.50. Okay, for 3, write an equation that gives the amount of money Adrian will earn, y, in terms of the number of hours since Samson started working. Well, he's also making 7 an hour, but he's starting 90 minutes later. So that amount of money that he's starting behind, we just solved for in the previous question. So he's starting $10.50 behind Samson. So that equation will give the amount of money he's earned. So 4, how much money will each student earn by noon? Well, if they started at 7, noon is 5 hours away. So Samson, 7 times 5, he will have made $35. And then Adrian, 7 times 5 minus 10.5. At noon, he will have made $24.50. So he'll be $10.50 behind Samson. Okay, 5 wants to know, will Adrian ever earn as much money as Samson? Well, he started 90 minutes behind. He's always going to be 90 minutes behind in his earnings, so no. He will always be $10.50 behind Samson. So if we want to write a system of linear equations for this problem, our two equations we wrote are our system of equations. So y equals 7x, and that's Samson's equation. And then Adrian's was y equals 7x minus 10.5. So analyze the system of linear equations. What do we know about the solution of systems by looking at the equations? Well, we know if we look at the slopes, they have the same slopes. So they will never touch, so there should be no solution. Because if we were to graph those two lines, they're never going to touch. Okay, so it says, let's see what happens when we solve that system algebraically now. Since both of them are written in slope-intercept form, we can substitute one expression for the first equation into the second equation. In other words, I'm going to go back up here, and I'm going to plug in 7x for the y. We're going to substitute that in there. So we have 7x equals 7x minus 10.5. So if we were to try to solve that and subtract 7x, we're going to end up with 0 equals negative 10.5. Well, that's not true. So x has disappeared from the equation, and we end up with a mathematically untrue statement of 0 equals negative 10.5. So does our result for x make sense? No. We can just say because 0 does not equal negative 10.5. So knowing that now, as we move on to the next page, number 9, what is the result when we algebraically solve a linear system that contains parallel lines? The result, mathematically, a false statement. Which means no solutions. So there is no point, no x and y value we can plug in to satisfy those two equations. All right, so now we're going to look at what's basically the opposite of that. So on Monday night, the fair is running a special for the local schools. If tickets are purchased from school, you can buy student tickets for $4, adult tickets for $4 also. You buy 5 tickets and spend $20. So we're going to write an equation that relates the number of student tickets, x, and the number of adult tickets, y, to the total amount spent. Well, they're both $4, so we're going to have 4x plus 4y equals 20. And then it says we bought 5 tickets. So we could say just x plus y equals 5 total tickets. Okay, well, there's our system. And actually, that would have been the answer to number 11. I was skipping ahead. Let me write that down here. So x plus y equals 5. So there's the equation that relates the number of student tickets, x, and the number of adult tickets to the total number of tickets purchased. So it wants us to now write both equations in slope-intercept form. Well, for 4x plus 4y equals 20, if we solve for y, we're going to subtract 4x and then divide by 4, and we get y equals 5 minus 1x. And then for the other equation, be a little quicker, x plus y equals 5. We just got to subtract x. We get y equals 5 minus x. Now, if we analyze that, if you might notice now, we are left with the exact same equation. Y equals 5 minus x, or negative x plus 5 if you wrote it the other way. So what do we know about solutions to the system looking at those equations? It's the exact same line. So that's going to result in infinite solutions. Every single point on the line would be a solution because one line is essentially on top of the other line. It's the same line. Okay, so since both are now written in slope-intercept form as the expressions for y in terms of x, substitute the expression from the first equation to the second equation. So essentially we're going to prove now that there's infinite solutions. So if we set those equal to each other now, 5 minus x, substituting that in, equals 5 minus x. Again, if we try to solve by adding x to both sides, our x's cancel, and we end up with 5 equals 5. Well, that is a true statement. So does the result for x make sense in this case? Yes. Every x value you plug in, the solution will be true. No matter what x we plug in, it's going to work out to give us a true statement. So how many student tickets and adult tickets did you purchase? Any combination would work. So I'd just say any combo would work. You could purchase 1 student, 4 adult, 2 student, 3 adults, 3 students, 2 adults, or any combination of 5 would work. So 16, what is the result when we algebraically solve a linear system that contains 2 lines that are actually the same? The result would be a mathematically true statement. Which means there are infinite solutions. All right, solving a system still by substitution, just more practice here. Another example. So it says the admission fee for the fair includes parking, amusement rides, and admission to all commercial, agriculture, and judging exhibits. The cost for general admission is $7, and the cost for the price for children under the age of 5 is $4. And there were 449 people who attended the county fair on Thursday. The admission fees collected amounted to $2,768. So we're going to write a system of equations in standard form for this for apply to this situation. So first, I call it the money equation. We're dealing with money here. I'm going to write an equation for all the values of money involved. So it tells us that they want to use x to represent number of people 5 and over. So the general admission crowd. So those are 7. So 7x plus 4y equals 2,768. And then we could just, for the number total of tickets, we could say x plus y equals 449. Okay, so B, without solving the system of linear equations, interpret the solution. Well, the solution is going to give the number of children and general admission. Should say children under 5, but we'll just leave it at children, and general admission people attending the fair. All right, so now we're going to solve that system. So I'm going to solve one of the equations for y and then plug that into our other equation. So I'm going to take the one easiest to solve for y. So we'd subtract x, and now I have y equals 449 minus x. Okay, in our other equation, I'm going to write that in black here, 7x plus 4y equals 2,768. And I'm going to go substitute in 449 minus x for the y value. So I got 7x plus 4 times 449 minus x equals 2,768. So now all we have is an x variable to solve for. So we're going to need to distribute. 4 times 449 gives you 1,796. 4 times negative x minus 4x equals 2,768. So when we combine our like terms, 7 minus 4 for the x's, we get 3x. 2 more steps, subtract over our 1,796. So now we have 3x equals 972 when you subtract those, and then divide finally by 3. And we're going to get x equals 324. So our x, the number of people 5 and over, is 324. Now, that's the most work. When we plug it back in, it'll go quicker now. So if we plug that in, y equals 449 minus x, which we now know is 324, we can subtract there, and we'll find that y, the number of children 5 and under, is 125. So there's the solution to our system. X is 324 for our general admission, and then y is 125. All right, next page, we're going to look at another example. Same idea, just different problem. So the business manager for a band must make $236,000 from ticket sales to cover costs and make a reasonable profit. The auditorium where the band will play has 4,000 seats with 2,800 seats on the main level and 1,200 on the upper level. Attendees will pay $20 more for the main level seats. So we're going to write a system again. X is going to represent the cost of main level. Y is going to represent the cost of the upper level. So for the main level, 2,800 on the main level plus 1,200 on the upper level, y equals 236,000 total. And then we could write a second equation. It says they'll pay $20 more for main level seats. So the main level is equal to the upper level plus 20. Okay, so there's our system. So B, without solving, what is our solution going to represent? It's the cost of main level and upper level tickets. All right, so again, we are going to substitute. This one already sets up perfect for substitution. We're going to plug in y plus 20 for x in the first equation. So 2,800 times y plus 20, substituting for that x, plus 1,200 times y equals 236,000. Squeeze that in there. I'll move it over to the left for the next step. So if we distribute now, we get 2,800y plus 20 times 2,800 would be 56,000. Bring down everything else. Combine our like terms. 1,200y plus 2,800y combines to be 4,000y. So a lot of zeros here. Just be careful with those. Subtract over the 56,000. And now we end up with 4,000y equals 236,000 minus 56,000 is 180,000, and divide by 4,000. And we're going to find y. The cost of the upper level seats would be $45. And then again, if we want to plug that back in, plug it into this one here. That's x equals y plus 20. Be the easiest one to plug it into. Either one would work. That's just the easiest. So y plus 20, 45 plus 20. And we're going to find that x, the cost of main level tickets, erased again. Again, if you need to go back and find that, just rewind the video, but that was 65 and x was 45. I accidentally hit that delete button again. Okay, but again, you can rewind it and get all that filled in if you had not completed that quite yet. All right, third one. Miss Ross told her class tomorrow's math test will have 20 questions and be worth 100 points. Multiple choice questions are 3 point each. Open-ended response questions will be 8 point each. Determine how many multiple choice and open-ended response questions there are. Okay, well, total there's 20 questions we know. So we could say x plus y equals 20. And then we know there are 3 point questions. So 3x, 8 point questions, y, those are the open-ended questions, equals 100 total points. Okay, so this solution will represent the number. I'm just going to put number of multiple choice and number of open-ended questions. All right, so if we want to solve this, again, we need one of those equations solved for y. I'm going to solve this one for y. So if I subtract x, I get y equals 20 minus x. Now I'm going to go substitute that in for the y in my other equation. So 3x plus 8 times 20 minus x equals 100. And we're going to solve for x now. So again, we would distribute. So 8 times 20 gives you 160, and then minus 8x. Combine your like terms. 3 minus 8 gives you negative 5x. And then we're going to subtract 160. So we end up with negative 5x equals negative 60, and then finally divide by negative 5. So x, the number of 3-point questions, would be 12. And then if we plug that back in, y equals 20 minus 12. So the 8-point open-ended questions, there would be 8 of. So 20 total questions when we add 8 and 12 together. All right, so we are going to skip all the way now to just the examples at the end. A few more, just solving systems of equations, a few more practice questions. Not application to situations, just given the equations, and we're going to solve using substitution. So for the first one, A, we have y equals 5x, so we're going to substitute in 5x for that y. So we have 2x plus 3 times 5x takes the place of the y equals 34. So then we can multiply. 3 times 5x gives us 15x. Combine our like terms, so we get 17x equals 34, and then divide by 17. So x would be equal to 2. And then if we plug that back in, the easiest one to plug it into would be the y equals 5x. So y equals 5 times 2, and we get y equals 10. Okay, so there's one example. Now might be a good time to pause the video, try the next 3, and then you can check your work. Okay, so for B, switch colors so you don't get confused. They're both equal to y, so I'm just going to substitute the 3x minus 2 for the y here. 3x minus 2 equals 4x plus 2. Solve that system. I'm going to subtract 3x. So we get negative 2 equals 4 minus 3, so 1x plus 2, and then subtract our 2 over to isolate the x, and we get x equals negative 4. And again, on this one, really neither equation is faster than the other one to plug it into, so you just pick which one you want. I'm going to use the second one. So y equals 3 times negative 4 minus 2. And when we simplify that, we're going to get negative 14 for the y. Okay, and then for the next one, neither one of those is solved for y, so we're going to need to solve one of them for y. I'm going to choose that second one. So I'm going to subtract the 2x over, and I get negative y equals negative 2x plus 5. And then divide everything by negative 1 to get positive y, and we're going to get y equals 2x minus 5. So now I can substitute 2x minus 5 for that y. So I got 3x plus 2 times 2x minus 5 equals 4. So again, distribute, and you get 3x plus 4x minus 10. Combine your like terms, and we get 7x minus 10. Last two steps, add over the 10, and we end up with 7x equals 14, and then divide by 7. So we got x is 2 on that one. And then when we plug it back in, if x is 2, 2 times 2 minus 5. And you're going to end up with y is negative 1. And then finally, the last one, again, we need to solve one of those equations for y. That first equation is going to be the easier one to solve. If we just subtract 3x over, we get y equals negative 3x plus 8. So if we go plug that in now for the y here, I did it again. Let me rewrite that. Y equals, again, you can always rewind the video to see what was there. Negative 3x plus 8. Sometimes I accidentally hit that delete button. All right, so we're going to plug that in here for that y. So we have 6x plus 2 times negative 3x plus 8 equals 10. Again, so we're going to solve for x. So we distribute, which gives you 16. Now here, look what happens. 6 minus 6 is 0. So we end up with 16 equals 10, which is not a true statement. And if you remember from earlier in the lesson, when that happens, a mathematically false statement, that means we have no solution. So there's no point that would satisfy that system of equations. All right, so next lesson we'll look more into systems now that we've seen our first method of solving by substitution.